Electrophilic addition reactions. Electrophile, an electron deficit species that can accept electron pairs from a nucleophile. Remember that nucleophiles have a lone pair of electrons that are capable of forming dative covalent bonds. Electrophiles can also be called Lewis acids, which is something that you'll learn about in IB Chem 2. Electrophilic substitution of benzene. Unlike alkenes, the resonance bonding in the benzene ring is quite hard to break and will not undergo addition reactions. If you were to look at the benzene ring as drawn like this, it would kind of look like you could just add across the double bond just like any other alkene. But we don't have that in benzene. We have resonance. The double bond, single bond is not what we have. We have resonance. To look at resonance in a little bit more detail, each of the carbons has a sigma bond between them, but the additional bond, the additional double bond, is the overlapping of sp3 hybridized orbitals both above and below the plane of the benzene ring. And so when we talk about the resonance, this circle here, what does it represent? It represents this flow of electrons between the upper and lower lobes of the sp3 hybridized orbitals that are overlapping. Now, all of this is to say that we can't break the bonding between the carbons in a benzene ring like we would think looking at it drawn like this. So we can't add across carbons. So addition, not on the table. But substitution is. Benzene rings can undergo substitution reaction. So for example, the chlorine can be substituted in for a few of the hydrogens on the benzene ring. Now remember that benzene, or the formula for benzene is C6H6. You have 6 carbon atoms and 6 hydrogen atoms. Each one of these carbons has a hydrogen on it. So in this reaction, 2 of the hydrogens have been replaced with chlorine. Nitration of benzene. Overall reaction. So this is the reaction we're going to look at in more detail. This is concentrated nitric acid, concentrated sulfuric acid. We warm it up a little bit and we make this molecule. Now the NO2 is called nitro and this is called nitrobenzene. So how do we make this? It takes place in a series of 3 steps and we'll pull back the curtain and see how this is done. Step 1. The sulfuric acid protonates the nitric acid, which forms the nitronium ion. And this happens by taking sulfuric acid, mixing it with nitric acid, and because sulfuric acid is the stronger of the 2 acids, it will protonate nitric acid. So we end up with the bisulfate ion and the nitric acid with an additional hydrogen on it, so it's protonated. But this is very unstable, and it immediately decomposes to form water and the nitronium ion. This is our electrophile that we need. So this entire step was to make this. The resonance electrons in the benzene ring are attracted to the nitronium electrophile. A covalent bond forms with one of the ring's carbon atoms. So I've just highlighted the bonding between 2 carbons. And I'm using the double bond here because it's better way of illustrating what is going to occur here. So one of the carbons, I'll pick this carbon, is going to form a covalent bond with the nitronium. Now remember that that carbon also had a hydrogen on it as well as all the other carbons, and so that's this hydrogen here. So this carbon has 4 bonds, but this carbon here has lost the bond that additional bond that it had with this carbon, and so we have a positive charge here. The electron that it was sharing is now going to the nitronium ion. So this is a carbocation, and remember carbocations are very reactive. The third step, the bisulfate ion, which was from step 1, remember, one of the lone pairs on an oxygen will form a dative covalent bond with the hydrogen. It'll have a stronger attraction for the hydrogen than does this carbon. So it'll be plucked away and reform sulfuric acid. In so doing, we now have 2 electrons that can reform the bond with this carbon, which is what occurs. And there we have it. This is nitrobenzene. This is the compound that we are interested in making. Nitrobenzene, the nitrogen has resonance between two oxygen atoms. This is very reactive. Approximately 95% of nitrobenzene is consumed in the production of aniline. Aniline is nitrobenzene where the oxygens have been replaced with hydrogen. Now, as you can see, nitrobenzene in and of itself is not really used for much. 95% of its production is solely to make aniline, which is a really important chemical. Aniline is a precursor to urethane polymers, rubber chemicals, pesticides, dyes, pharmaceuticals, and explosives, a very important industrial chemical. Another important benzene compound is methylbenzene. The preferred IUPAC name for it is toluene. This too can undergo nitration to form 2,4,6-trinitromethylbenzene. So we have 3 nitros on it. Now, by definition, the methyl, the carbon that has the methyl, is defined to be carbon number 1, so that's why we don't need a number to designate where the methyl is. The IUPAC preferred name is 2,4,6-trinitrotoluene. However, it has a much more common name that you probably have heard of. And here's a big hint. It is TNT, which stands for trinitrotoluene. Okay, that is it. That is the end of notes, the end of this unit.